Hi, my name is Winnie. I'm currently a PhD student at Rice University, working with my advisor, Dr. Anki Patel. Today I'm going to present our work and towards a better understanding and regularization of GAN training dynamics. So let me first introduce the background. GANs are a class of very powerful generative models. So in GAN framework, there are two neural networks. One is the generator, the other one is discriminator. Generator takes noise as input and output fake samples. Discriminator will take two types of samples, real samples and fake samples, and try to differentiate is real or fake. So during this computing process, we hope the generator can learn to generate realistic samples. And normally GAN can be formulated as a minimax game. So the discriminator trying to maximize the payoff function f, and the generator tries to minimize the same payoff function. So during backpropagation, the gradient updates normally use simultaneous gradient in GANs called SimGD for short. So in SimGD, generator trying to do gradient descent and discriminator does gradient ascent autonomously. Although GAN has achieved a great access in generating realistic samples, but still it's an open question to understand the training dynamics of GANs. In general, global convergence analysis is impossible without some unrealistic assumption like convex concave. But by following the same argument from previous work, we think it's necessary to first analyze some local convergence behavior near equilibrium. So by saying local convergence, we mean how fast it takes initial point near equilibrium to reach the equilibrium point. So in this work, we first analyze the Jacobian properties and trying to see how the Jacobian properties impact the training dynamics. So we first consider a simple GAN example. Basically, it's a linear GAN to transform the latent Gaussian Z with zero mean to real Gaussian with non-zero mean V. And by saying linear GAN, we mean both discriminator and generator are linear function of the input. So this is a very simple case. And with some parameterization, we can transform the equilibrium point to the origin for the ease of our later analysis. And since we focus on Jacobian, then the definition of Jacobian of SimD is given in this form. And we want to emphasize that in GANs, the Jacobian is not symmetric, which makes GAN quite unique to the other neural network-related optimization problem, because the traditional neural network optimization is more like the Jacobian should be symmetric. And after that, the eigenvalues of Jacobian of trained by SimGD is given in this theorem. And we can see that the properties of eigenvalues now depend on the data distribution parameters. So after that, we can provide the local convergence behavior in this simple GAN example. And our analysis is divided into two cases, complex or real eigenvalues. So first of all, if there exist complex eigenvalues, we can show that the training steps for convergence increase quadratically with the imaginary to real ratio represented by zeta here. And if there exist real eigenvalues, then the training steps for convergence increase linearly with the condition number represented by tau here. So here it comes to the main result. There may exist the following two factors of the Jacobian GANs simultaneous that result in the GAN training issues. The first one is the phase factor which means the Jacobian has complex eigenvalue with a large imaginary to real ratio. The second one is a conditioning factor, which means the Jacobian is yield conditioned. So we think these two factors are the main cause of the GAN training issues. So for example, in the simple GAN example, we can show that the data distribution parameter, the mean and covariance, can control the impact of two factors. And we can show that both of them should not be too small or too large. Otherwise, either phase factor or condition factor may dominate the training issues. And we think this is a relatively strict requirement for local convergence in GANs. And this may explain some training instability issues. So how to improve the GAN training issue? And we trying to propose a new regularization method called JRAR. And so in JRAR, the generator and discriminator updates are given in these two equations. So basically, we introduce two regularization methods in both generator and discriminator. And for generator, basically, it tries to minimize the square of the norm of the discriminator gradient. And similarly, discriminator trying to also minimize the square of the norm of the generator gradient. And also the hyperparameter gamma controls the gradient terms. And the eigenvalues of the regularized Jacobian trained by JRAR is given in this theorem. And we can show that the properties of the eigenvalues now depend on the hyperparameter gamma. So, which means we can tune the hyperparameter gamma to see if we can alleviate these two factors. And our further analysis shows that if in the limit of gamma goes to infinity, we get the imaginary to real ratio to 0 and the condition number to 1, which means there's no complex eigenvalue and the Jacobian is well conditioned, which means the JRAR can alleviate the two factors by construction here. The problem with this previous analysis is that we only focus on the simple GAN example, and we also want to extend our analysis to the general case. But before that, we need two assumptions. The first one is that in the equilibrium, we require the generator distribution is the same with real data distribution, and also the discriminator cannot differentiate it's real or fake. Basically, this is just trying to make sure we are considering the optimal equilibrium point. And we also introduce the other assumption just to avoid some trivial solutions. So after that, we can give the Jacobian of general GANs trained by CMGD. So here, the Jacobian now is depending on two auxiliary matrices, P and Q, and they are given in these two equations. In terms of the physical meaning of P and Q, we can see that P now represents how sensitive that discriminator is to the local updates of generator, and Q represents the local geometry of a discriminator, which is quite similar to the definition of phase information. So the Jacobian of the eigenvalues of Jacobian trained by CMGD is provided in this theorem. And now the eigenvalue is a function of two scalars. One is A1 and A2. A1 and A2 are some convex combinations of eigenvalues Q and P transpose P. Our further analysis shows that we require Q and P transpose P. Both are well conditioned, which requires good generator and discriminator actors, and they both have similar eigenvalues, which require discriminator should well match generator so that we can avoid the two factors we identified before. We think this is a quite strong requirement for GANs. to satisfy. So how about the eigenvalues of the Jacob being trained by JRAR? Here we found that it's quite interesting that in the limit of gamma goes to infinity, the eigenvalue trained by JRAR now it only depends on P transpose P, which means the imbalance between eigenvalues of Q and P transpose P will not be an issue in general GANs if trained by JRAR. So in summary, this table shows the requirements for both SIMGD and the JRAR in terms of ensuring good local training dynamics. And we found that for stable SIMGD, it requires Q is well conditioned, P transpose P is well conditioned, and also Q should match P transpose P. But for stable JRAR, we only require P transpose P is well conditioned. So we argue that JRAR should be easier to train with better robustness than SIMGD. So next, we do some experiments to verify our analysis. The first one is isotropic Gaussians, which are exactly the setup we have done in our analysis. So this one just to verify our analysis directly. And here we provided both discriminator and generator training curves, and we compare three GAN models, SIMGD, CONAPT, and CONAPT is a very similar regularization method proposed before, and our proposed method, JR. We found that SIMGD SIMGD denoted by the blue curves will oscillate and it's difficult to converge. So we think SIMGD suffers from both phase and the conditioning factor. And CONAPT, represented by the orange curves, especially for its generator training curve, it's difficult for it to converge. So CONAPT suffers from conditioning factor, and only our proposed JRAR can have a decent convergence rate. The next experiment is a mixture of Gaussians, which is quite standard setup for GANs. And we also compared these three models, SIMGD, CONAPT, and JRAR. And over iterations, we can see only SIMGD oscillates among different modes and fails to converge, and CONAPT and our proposed JRAR can converge well. And our last experiments on the real data set, CEPA10, and we compute inception score and FID. For inception score, the high is better. For FID, low is better. And we evaluate 4 models: the original GAN, CONAPT, and the SN GAN, spectral, which is a spectral normalized GAN, and it's a stable model last year, and JRAR. And we trained this 4 models and 6 different network actors and to see the robustness of different GANs, and we found JRAR is more robust than previous methods across these different settings. And we also show some generated results, samples from different GANs and across different training settings. Visually, JRAR is able to generate good samples across these different settings, but the other GANs, they may generate some poor images in 1 or 2 cases. Okay, thank you.